So, I'd like to take you back to the dawn of the age of computer storage. And I mean this quite literally. When programmers think about bits, we typically represent them symbolically as a series of zeros and ones. Tom Stewart had a slide similar to this in his talk yesterday. But bits are not actually zeros and ones. They are, in fact, electronic components, real physical things that you can touch. And in the beginning, a mere 67 years ago, there was only one of them, and it looked like this. This is a replica of the world's first transistor. Now, if you've done any work or play with electronics, this may be a more familiar picture of a transistor. It has 3 terminals. That's characteristic of a transistor. And this is the symbolic representation of a transistor. One terminal is called the collector, or the drain. One is called the base, or the source. And the last is called the emitter, or the gate. I like that each one has 2 different names to make it really confusing. So the way this works is if you take a power source, let's say a battery, and you connect the negative terminal to the base and the positive terminal to the collector, nothing happens. That's basically the equivalent of a 0. But as soon as you touch the collector to the emitter, electrons will start flowing from the negative terminal of the battery through to the base of the emitter and from the collector to the emitter with a higher amperage. Now, quick show of hands. How many people understood how a transistor worked before I just explained it? Okay, hands down. How many people still don't understand what it is after I've explained it? So, few of you, thank you for your honesty. So the good news is it doesn't really matter. You don't need to understand how a transistor works to use or program a computer. And the thing that makes this possible is something called abstraction. What is abstraction? Well, I'd like to share a quote by John Locke from his essay concerning human understanding from the year 1690. And he said there are 3 main things the mind is capable of. Number 1, combining several simple ideas, 2 or more simple ideas, to create a complex idea. Second, he says you can take 2 ideas and not necessarily combine them, but just sort of put them next to each other and sort of compare and contrast. And the product of this exercise is understanding the relationship between these 2 ideas. And third, the third main thing the mind is capable of, according to Locke, is abstraction. Basically, you can take a concrete idea and generalize it. So that's Locke's definition. This is mine. So in the same way that we can all use and program computers without necessarily understanding how the fundamental pieces work, how each layer below the level we're programming at works, we're able to do it anyway. When software developers think about a bit, we don't think about something that looks like this or like this. Maybe we think about something that looks like this. You don't need to understand how a transistor works to understand that it functions as a switch that can be off or on. And we can abstract that to a symbolic representation of a 0 for off and a 1 for on. By giving hardware bits a symbolic notation of 0 and 1, it also allows us to start using bits as counters. Unfortunately, we can only count up to 1, which is not that useful. If we want to count higher than 1, we need to give our bits some structure. This brings us to our next abstraction, the byte. Bytes free us from having to think about individual bits, individual 1s and 0s. Instead, we can think about numbers between 0 and 255. Once we've done that, it's a short step to map those numbers to letters, punctuation, and other characters. Abstraction not only allows us to work with things without understanding them, it allows us to reason about problems at a higher level. Instead of worrying about the individual bits, we can think about things in terms that are understandable to us, like letters. And we can look at these letters and get some sort of intuitive human feeling about what they mean, as opposed to the bits, which are only meaningful to the computer. We used to program computers like this. telling the computer which individual switches it should turn on or off with the punch card. In some third world countries, such as Florida, voting is still done this way. This is some x86 assembly code that I actually also borrowed from Tom's talk yesterday. And it's definitely higher level than writing zeros and ones, but it's still tied to a specific computer architecture. And you're programming specific registers and specific addresses. Instead of referring specifically to memory, why not give that memory address a name that makes sense to a person? So variables are abstraction over reference. Languages with variables tend to be more abstract than languages without variables. And I think this is an improvement. Almost all programming languages have variables. It's a nice abstraction, a useful abstraction, better than this. Strings are an abstraction over character arrays. Not all programming languages have have strings. Some of them just have character arrays. And the array sizes can only be constants. This means we run the risk of a buffer overflow, since we have to try to guess in advance how many characters we need. There's also that annoying null terminator that goes at the end. And there's a whole category of bugs that can be caused by either forgetting to add a null terminator to your character array, or by trying to add things to the character array after the null terminator. That won't work. So strings, again, are an abstraction that let you operate on a higher level. I think they're quite a nice one. Does anyone know what the C program will output? A hint. That number, I, stored in the int I, is max int, or int max. So when we add 1 to it, any guesses? Yeah. You'll get negative 2,147,483,648. That's not very user-friendly, right? In Ruby, we don't have this problem. We have fixed nums, and when we overflow fixed nums, we get big nums. And we don't really need to understand that distinction. In my view, Ruby could even hide away that distinction and just have something called num or integer, and take care of whether it's a fixed num or big num under the hood, right? Not really important to you. You don't need to know the difference. And as a result, you can sort of have infinitely long numbers in Ruby, or it's only constrained by the amount of memory that you have, not by some arbitrary type constraint. So functions are abstractions as well. They're abstractions over behavior. And languages that allow you to define functions, I would argue, are more abstract than languages without functions. It's, again, not such a controversial statement. I think functions are quite popular in programming languages, so it's good. But blocks are not, right? Not every language has blocks or closures. And this is a high-level feature that's quite nice. Again, I would argue that the thing that blocks allow you to do is define behavior on the fly. And if you look at most Ruby DSLs, the way they work is heavily tied into using blocks, right? Something like RSpec, you're using blocks all the time to define your tests. And so the idea of basically defining a domain-specific language in another language, Ruby, it leverages this feature in Ruby so that you can operate at a higher level, the level of your test domain, for example. Or Sinatra allows you to operate sort of in the HTTP domain using blocks. So again, I would argue that languages that require you to manage memory manually are less abstract. Languages that perform garbage collection are more abstract. So this is terrible, basically. If you try to, if you call that free twice instead of once somewhere later on, then you'll get an error. And if you try to access a pointer that's already been freed, you get an error. There's a whole class of errors that can basically be solved by getting rid of manual memory management and having garbage collection instead. So Grace Hopper, a programming language designer, she worked on COBOL. She believed that programs should be written in a language that was close to English. And So I just want to sort of take you through what I consider to be sort of the history of programming languages, just so you can sort of see this trajectory, because I think there are some trends and lessons that can be learned from this. And this chart, it's basically just one very dynamic slide, but don't worry too much about the y-axis. It's not labeled. Just think about it sort of as the values of being relative. So if one programming language is above another, that means it's more abstract. We won't say how much more because these things are hard to quantify, but I think you can make a pretty clear case just in the ranking, basically. Forget about the magnitude. So at the most basic level, the first computers, we had machine language. And shortly after that, we developed assembly language, again, specific to a particular hardware architecture, and talking directly to registers and addresses. Then, a few years later, I believe it was 1958, we got Lisp. And Lisp was much higher level than assembly language. Again, don't worry too much about the magnitude, but I think it's fair to say Lisp was at least 1 or 2 orders of magnitude more abstract than assembly language, which itself was more abstract than machine language. And so I would call this progress. And the year after Lisp was released, we got a language called COBOL. This was Grace Hopper's language that she was working on. And in 1960, we got ALGOL, which is, yeah, similar to COBOL and Ruby, actually. There's certain Ruby syntax that can trace its roots back to ALGOL. And COBOL and ALGOL are interesting because they were the first 2 languages that tried to define a language standard and to try to basically say that the language itself conforms to a particular standard that people can write to, which I would argue is a form of abstraction because by sort of locking down a standard, it means that you can then use that language across different hardware architectures, which at the time was not, hardware was sort of widely varied. So if you could standardize on the language and abstract across the hardware, this was a very nice feature. So standardization was sort of, I would say, the big step forward for COBOL and ALGOL. And then a few years after that, in the mid-60s, Simula was released. Simula is the world's first object-oriented programming language. And again, I think you could trace some of Ruby's roots back to Simula. And it never really got very popular, but it had many of the sort of object-oriented features that inspired languages to come. Then came C in 1970. And C, I would argue, is a very low-level language. It's basically one level above assembly language. It's standardized and sort of abstract across different hardware architectures, portable across different hardware architectures as long as there's a C compiler. It doesn't have anything specific about the architecture encoded into the language the way assembly language does. But I would say this was a bit of a step backward in terms of abstraction. That said, compared to all of these other languages, Simula, COBOL, ALGOL, and Lisp, C was really popular and continues to be popular relative to these other languages. It's arguably the most popular language still today. And I think the reason why C became so popular was because it gave you a certain amount of control that you really needed back then, right? These abstractions actually have a cost. And the cost is that if you're writing code, if you're sort of optimizing the language for a human instead of for a computer, it's not going to be as efficient. And so C, by sort of writing code that's optimized for a computer, allows you to get performance in an age, really good performance for really low-level systems in an age when hardware was very, very sort of slow and constrained, right? Memory was constrained. You had very few CPU cycles. So yeah, C became really popular in this environment and continues to be popular today. The other thing about this time is there wasn't that much code, so almost all code, by definition, was low-level code. People were writing the first operating systems, the first servers, right? People weren't building web applications because the web didn't even exist yet, right? So people weren't building games and things like that. So having C and having the control over over the language and having a little bit more abstraction than assembly language, but still having a similar degree of control, C sort of hit the sweet spot for 1970 and really began to take off. But then a few years later, SmallTalk came around, and SmallTalk took some of the object-oriented concepts from Simula and built on those, and again, shares its ancestry with Ruby. It never became as popular as C, but I think it's a very significant language, and at the time, again, continued this trajectory after the step backwards to C, continued the trajectory of more abstract languages over time. So then in 1983, the year I was born, C++ came out. And this took some of the sort of high-level concepts, some of the object-oriented principles from SmallTalk, and brought them, SmallTalk and Simula as well, I guess, and brought them to a C-like language, right? But it did that in a way that was trying to be compatible with C. So basically, it gave you objects. It sort of added some new features to C. It was C++, quite literally, adding some object-oriented features, but not necessarily abstracting away those low-level details. So you still had the same control as C, but with this sort of new idea of objects. And ObjectiveC came out around the same time, and I would say was another attempt sort of at making a better C, an object-oriented C. Then, I believe it was 1991, Python came out. And Python was really a big leap forward towards more abstract programming languages. It was it had sort of more object-oriented features than any of the previous languages, and it didn't have all that sort of baggage that came along with C or C++ or ObjectiveC. It was a wholly new thing. And it was sort of a scripting language, so you didn't even have to compile code, right? You could just sort of run it on the fly, and that was true of some earlier languages as well. And Perl also came out around then, although at the time when Perl was first released, it wasn't object-oriented. So I would actually rank that below SmallTalk on this scale. Then 1995 was a crazy year. So this was the year that probably the most significant year of programming language release. Well, yeah, it was a very significant year. So this was the year that Ruby was released. It was also the year that JavaScript was released, also the year that Java was finally released. And I sort of slotted these in. Ruby is kind of up there with Python. I put it above Python because I'm biased in that way. JavaScript is also a very high-level language. And Java is cool because it actually runs, like the sort of innovation with Java is that it doesn't actually output machine code. There's a Java virtual machine. And the way Java was able to gain portability across systems was not by having a compiler for every single system, but to have a virtual machine for every single system and then running code on top of a virtual machine. And I think that was only really made possible in the mid-90s when hardware got to a point where you could conceive of running a virtual machine on top of actual hardware. And Java also created a platform with this virtual machine, right? So in the early 2000s, Scala came out, and it was basically trying to be a better Java, right? Java, but without some of it sort of looked at the mistakes that Java made in its design and tried to avoid some of those. And I think did so successfully. I would say Scala is a higher level language than Java and probably better in most ways. Clojure is another one of these languages. So for me, I sort of think of Clojure as a better Lisp. And again, it has more abstract concepts, more primitives. It's sort of a full-featured practical Lisp. And again, hosted on this Java virtual machine, which is quite a nice platform. Another trend upward, so Go. This is getting into relatively modern history, right? I think Go was released in 2009 or something like that. And you know, Go is a lower level language than almost all of the ones on this list, but it's not really trying to be a high level language. Go is trying to be sort of in their manifesto like a better C++. They designed it because people were still writing C++ in 2009 and they thought that was ridiculous. People should have something better after all these years. And so you can look at Go as being a low level language, when compared sort of relative to the thing it was intended to replace, C++, it's higher level. It has garbage collection built in. You don't have to do manual memory management, things like that. There's other ways actually in which Go is lower level, right? So it doesn't have a lot of the object-oriented features that C++ has. But overall, I would say it's a higher level language. And then Rust I would put in beneath Go because it doesn't have a garbage collector, for example. But again, it's a lower level language when compared to Ruby and Python, but higher level when compared to C. So I think we see this trajectory over time of languages getting higher and higher and higher level. There's one more, sorry. So Swift, again, follows the same pattern of it's not higher level than Ruby, right? It's not trying to be a better Ruby. Swift is trying to be a better Objective-C. And I think achieving that goal. So over time, we're moving higher and higher and higher up this abstraction ladder, basically. But nobody's trying to make a better Ruby, right? People tried to make a better C. People have tried to make a better C++ in Go. People have tried to make a better Objective-C in Swift. But nobody's really attempting, or at least they haven't gotten so popular. There hasn't been much traction for attempts to make something that's more abstract than Ruby. And so the rest of this talk will basically be focused on that. Ruby is still the highest level programming language in the world, according to me. But I think there's a good argument to be made for that, right? It's maybe not the highest level in the world, but certainly the one, if you sort of take into account wide use and things like that. It's a very high level language. But it's 20 years old. It's over 20 years old now, right? It was released in 1994. And so I think if Ruby was being reinvented today, if somebody was creating a new programming language that sort of had the same design goals as Ruby, to be a high-level language, so you don't have to think about memory so much, manual memory management, things like that. A programming language that just sort of does things for you. These are sort of the things that I would do to make a higher-level language in 2015. I would kill symbol. So symbols are basically strings, but they never go away, right? So the idea is that like you can have a string, you can have a symbol, and if you compare it to another symbol, it's not allocating, like when you create another symbol or when you reference that symbol again, it's not allocating new memory the way it would a string. It's just sort of pulling it out of the symbols table. So it's sort of this low-level thing, right? It's like this performance optimization. Every time you want to have a symbol, you don't need to like allocate new memory the way you would with a string. You just sort of have it have a reference to it. But in Ruby 2.1, there is this new feature where you could freeze strings, and this is the description of it, and that's the issue number on the Ruby bug tracker. You can read the details. But basically, if you say literal.freeze, it will behave more or less like a symbol, right? So if I say some variable A equals string.freeze and some other variable B equals string.freeze, then these are actually referencing the same object. They have object identity, which was the whole point of symbols in the first place, right? Like this was the thing that symbols were basically trying to solve. And since Ruby 2.1, this has been solved in strings. So strings are sort of moving closer to symbols in this way. You can basically symbolize a string by calling toSym on it, or you can just call freeze, and it has this property if you do that. And then Ruby 2.2 came out a short while ago with this feature, symbol garbage collection, right? So the other remaining difference between strings and symbols was that strings would be garbage collected and symbols wouldn't. But this caused all sorts of problems where some user would have sort of this very long params hash, and Rails would turn each param into a symbol, right? And this was a big vulnerability. So Ruby said, like, that's too risky. We're going to deal with this. We're going to actually make symbols garbage collectible. But now they're becoming more like strings. So these two constructs, strings and symbols, are converging. And I think it's an optimization that might have made sense in the 90s, in the mid-90s, when Ruby was being developed. But it doesn't make sense anymore. And just to sort of take you back 20 years to remind you what it was like back then, in the mid-90s, when Ruby was being developed, laptops had 8 megabytes of RAM. The highest end Mac you could get had 8 megabytes of RAM. So today, like this laptop has 8 gigabytes of RAM. So that's 1,000 times as much. And I think we don't need to be as concerned about like little string-like things taking up memory. We have plenty of memory to spare, and it's pretty cheap. And we're garbage collecting it anyway, right? So it's fine. It's great. OK, so next on my sort of chopping block for Ruby is I would kill floats, which is to say I wouldn't get rid of them entirely, but I would have something better. I would have a better decimal class. Here's sort of the requisite Gary Bernhardt tweets that have to go in every presentation. These are mine. I have 2. So yeah, like I basically agree with this completely. Like float is not a general purpose programming construct. And maybe it made sense in the 80s when it was developed, but it really doesn't make sense anymore. We can have infinite precision decimal numbers. We have the memory to do that. We have the CPU cycles to do that. And there's all sorts of bugs, all sorts of categories of mistakes that happen because you're using floats that wouldn't happen if we had a more precise decimal. This is the next one. This was, so like the first tweet was from January, and yeah, this is like a couple weeks later. So yeah, he basically like, Gary Bernhardt quit programming, fake quit programming because of floats. Yeah, floats suck. So why do floats suck? Like for those who are not so familiar with the suckitude of floats, this is why they suck. So 0.1 plus 0.2 equals 0.3. That seems reasonable, but it's totally false. Why is it false? Because 0.1 plus 0.2 equals 0.300000004. And yeah, like you would think computers by this day and age would be smart enough to figure this out, but they're not. People get into all sorts of trouble by storing money in floats and losing money that way. Or so yeah, there's like basically these rounding errors can occur, and there's no reason for it, right? You could just have a money class with 2 digits of precision and maybe something like a currency attribute, right? Like that's quite nice, but that's not built into the language. That's not a primitive. And float is. And I think that's, it gives people incentives to do the wrong thing. And almost every programming language has this problem, by the way. This is not specific to Ruby. Ruby actually implemented a standard, the IEEE floating point, which was developed in 1985. So just to sort of take you back to 1985, I took you back to the mid-90s before. Now let me take you back to the mid-80s. In the mid-80s, the state-of-the-art computer was a Macintosh 512K. They put 512K in the name because they were bragging about how much RAM it had, 512K of RAM. It had 4 times as much as the 1984 Macintosh. So yeah, and it also had a 7.8338 megahertz processor. They didn't even round to the nearest megahertz. They're like, it is a 7.8338 megahertz processor. They needed a float to store the precision of the processor, ironically. So yeah, in 2015, like we're like rounding off hundreds of megahertz now, right? Let alone fractions of a megahertz. And I think we have infinite precision integers in Ruby, right? We have big nums that can get as big as they can get. So why can't we have infinite precision decimals? Next on the chopping block, nil. So how many people have seen this before? This is sort of Ruby's way of telling you you have a null pointer exception. And there's a solution called optionals, right? So you can have an optional type where you wrap things that might be nil in sort of this container object, and the programming language ensures you handle them correctly. This is a feature in Swift and many other modern programming languages with sort of better type systems. So again, sort of, yeah, like shout out to Tom and like his talk yesterday, like Ruby should have optionals and should not have nil, in my opinion. I think that would make it a better language. Typed arrays. So this is another thing that is, again, sort of building on what Tom talked about yesterday. So in Ruby, you have arrays that can be mixed, but there's a lot of advantages of being able to sort of declare a array of a specific type and then sort of limit adding things onto the end of that array to be of that specific type. And I just made up some syntax for my sort of proposed future programming language. Yeah, so this is how you would say an array of integers and an array of letters or strings, and it wouldn't let you, the programming language wouldn't let you append to that array something that is not of the correct type. This not only saves you from certain errors because it's actually quite common that you want arrays to be of uniform type. This is typical. It's quite odd that you'd have mixed type arrays. I would almost argue that this should be the default and that you should have something like a tuple for things of mixed type. But yeah, I think the other really nice thing about this is you can get a lot of performance optimizations. So it's both higher level, but lets you optimize code at a lower level. And the way you can optimize is if you know that everything in the array is of the same type, then when you want to index, like you want to get to the 1,000th element of the array, if you know that the array, everything in the array is an 32-bit integer, you just multiply 32 times 1,000, and then you can just jump right into the middle of the array. So it makes indexing really fast, which is great. And I think the next version of JavaScript, ES6, has this as a feature, and I really want Ruby to have it. I think it's a nice feature. Method overloading. So I was trying to think of a better example. It's a bit of a contrived way to calculate the area of a triangle. There's definitely simpler ways to do it. But if you have two sides and the inner degree, you can calculate the area of a triangle this way. And I thought it would basically be cool if you could specify the degrees or the sort of third argument either in degrees as an integer or radians as a decimal. Again, I'm using that of syntax that I just sort of made up. But yeah, the nice thing about this is, yeah, you can sort of dynamically dispatch to different methods that have the same name as long as they're of different types. And yeah, I think Elixir has this, and lots of other cool programming languages have this feature. And I would like Ruby to have it too, because I think it's quite nice. I think if you wanted to do this, otherwise, you would have to have some sort of ugly conditional code. And here you get to basically just call the area code, call the area method from within the area method. But it's not a recursive call. It's calling sort of the other version of itself after it converts radians into degrees. I think that's cool. You don't need any weird if statements or things in there figuring out what type of thing the last argument is. I think methods should return methods. So yeah, up until Ruby 2.1, method definitions return nil, which was totally useless. And in 2.1, they started returning their names as symbols, which is actually slightly better. But it would be even better if a method definition returned the method that they defined as a method object that you could then pass to another method, for example. So an example of doing this would be you could have a memoize class method, and you would define a method. The method would then return itself, pass itself to memoize, and yeah, I think that looks kind of cool. And you could actually even define things like private and protected this way as well, or public, I suppose. So yeah, I think those wouldn't even need to be keywords anymore. You could take those out of keywords and just make them methods that act on return methods. Unify Ruby function syntax. So this is a real bugaboo of mine. There's too many ways to define a function in Ruby. You can do it with the def keyword. You can also use the proc keyword, which is the same as proc.new. That has slightly different semantics from the lambda keyword, which is the same as the lambda, the stabby lambda. And then there's two different block syntaxes, right? So, and blocks behave like procs, except they're not objects. And you have to understand all of these differences, understand all the syntaxes and semantic differences and the subtleties between them. That just shouldn't be necessary, right? We should be able to unify these. I don't know if we can get it down to 1, but let's try to get it down to 2, I think would be quite nice. And I have a proposal for that. It's actually borrowed from JavaScript and I guess other languages. So JavaScript, the function keyword is function, so it's confusing that I use that as my function name. But basically, I think we should replace the proc keyword with def. And you can define an anonymous function by just saying def and then nothing. And then you just have the block body of the function. And that would return essentially a proc, but you could just call it a method. And this pairs nicely with my previous suggestion of methods returning methods. So that sort of makes it more consistent, and you don't have to worry about these sort of low-level details. Better concurrency primitives. So yeah, I think this is the last one. And basically, like if you want to do concurrency in Ruby, it normally looks something like this. And you're dealing with threads, and threads are like this operating system thing, right? So if you, let's say you have a collection that has like 1,000 items, that's going to spawn 1,000 threads, which, you know, your operating system will probably not deal with very well. And like the fact that you even have to know like what an OS thread or a green thread or whatever is bad. Like basically all you should have to do is say something like, take this code, item.process, and parallelize it. And maybe it will do something smart, like dispatch it to a thread pool that has like a fixed number of threads or something like that. There's a lot of nice concurrency primitives in other languages, actors, futures, promises, and I don't really care which one Ruby gets as long as it's better than thread. I guess the other thing that Ruby has is fiber, but yeah, like that's even worse because yeah, it's like not cooperative, so you have to schedule the fibers yourself. And to be honest, I'm not sure I've even ever, like, I'm a bit afraid of fibers. Like, I don't think I've ever used them, and I almost never see them used. I don't think they're actually that useful. But we need to do concurrency, right? Like, this is an important thing, and we shouldn't have to, like, concurrency is hard. We shouldn't have to think about it. We should have nice objects that abstract that away, so we can just say, like, parallelize this, and it works. So yeah, that's the talk. Thanks.